my face is anyhow distracting. It's not an added value. Yeah.
Well,
So we are live now, sir. I think we can begin.
yeah, we just start now.
Okay, excellent.
Okay. So, good afternoon, all of you. So this is for the session one. In our session one, the first talk will be delivered Professor Hans. So Professor Hans is a professor of the Antwerp Systems and Software Modeling Group within the Department of Mathematics and Computer Science at the University of the Antwerp in Belgium, where he is a founding members of the NEXOR Consortiums on the cyber physical systems. AnSyMo is a core research lab of Flanders make the strategy research centers for the Flemish manufacturing industry. In a variety project, often with the industrial partner, he develops and applies the model-based theory and techniques on the multi-paradigm modeling in application domain. And he is one of the pioneer of the MPM domain, and also diverse bioactivated sludge waste water treatment plant design and optimization, safe automotive software, and autonomic production plan in the context of Industry 4.0. So we'll be very happy that Professor Hans gives a keynote in our session one, and just transfer the entire stage into podium to Professor Hans.
Thank you, Soumyadip, and thank you to the organizers for giving me an opportunity to talk about multi-paradigm modeling for cyber-physical systems. I was listening to the introductions, the various speakers, and I must say that I'm particularly proud to be invited to speak here because, of course, the vision of bits of interdisciplinarity of science and engineering, combining science and engineering, is something which I believe in, and also the collaborative aspect I think is very important. So thank you very much for inviting me, and without further ado, I will turn off my video to save some bandwidth and switch to my screen. Okay. So my talk is about multi-paradigm modeling for cyber-physical systems, and maybe I should point out in the context of science and engineering, I'm originally a theoretical physicist. Then I worked on bioactivated sludge wastewater treatment, plant modeling, which is a bit of microbiology. I've worked in robotics. I've worked in many different domains, and I think that's also what multi-paradigm modeling is about. It's about almost everything you can imagine. And that's the daily reality of the systems we study, of the systems we build. Yeah. So it's already been mentioned, the cost action, it's a European network. It's an instrument of the European Commission to foster collaboration, to foster understanding. And for a number of years, 4 or 5 years, we've had a cost action on multi-paradigm modeling for cyber-physical systems, the title of this talk. And you see this is a nice group of researchers from all over Europe, extended Europe actually, getting together to try and to learn from each other, and to basically, in our case, look into what multi-paradigm modeling actually might be and how it might help in developing cyber-physical systems. Actually, part of the action was also about figuring out what cyber-physical systems might actually mean. And as you can see, we organize events such as, that's the picture below, as training schools, because our goal is also train the next generation of students in the very latest, newest techniques and to point them in a certain direction. Actually, on the left, you see, I said the extended Europe. It includes, for example, Turkey. All the countries in blue were member of this action. So what I will talk about is basically the topic of this cost action. And you will also hear other speakers, such as Professor Buchs and Rensink, who are somewhere in this picture also, who were also part of this cost action. Okay, but maybe it's time for some definitions, because these are what's in the name, of course. What is multi-paradigm modeling? What are cyber physical systems? Most of my talk will be about multi-paradigm modeling, and maybe even more about dealing with complexity. And we'll see that multi-paradigm modeling is a way of dealing with complexity, is trying to structure the many ways in which we deal with complexity. And what are cyber physical systems? The running definition, which we had during this cost action, was that cyber physical systems emerge from the networking of multi-physical, and that means mechanical, electrical, hydraulic, biochemical, and so forth, and computational, such as control, signal processing, logical inferencing, planning processes, often interacting with a highly uncertain environment, including human actors, which obviously lead to a lot of uncertainty in a socio-economic context. So this is very, very broad. And it also acknowledges, that last part, that it's not just technical, that the choices we make in the systems we engineer have an impact on our socio-economic fabric, and vice versa, of course. And I should point out that this cost action was focused on engineered systems. That doesn't mean that multi-paradigm modeling, the ideas behind multi-paradigm modeling, are not useful for science, and because at a very high level, one could argue that they're sort of each other's opposites. Science tries to understand how things work and come up with theories, models of how things work. And then engineering takes these models, let's say Newton's law, and applies them to build particular artifacts which satisfy requirements and of course they will be functional requirements, but there will also be cost requirements, safety requirements, and so forth. So mainly MPM for CPS is about engineered systems, but that doesn't mean that we can't use some of these multi-paradigm modeling techniques to do science also. And of course, as we know, these two constantly cross-fertilize each other, science and engineering. And that's why BITS is such a great place, or places, I should say, given that it's distributed, because these two are indeed combined. Okay, so this slide will come back a number of times. It's all about how to deal with complexity. Now, there are many definitions of complexity, and some people will argue that there is a difference between something that is complex and something that is complicated. Complex often refers to the fact that there are lots of components, whereas complicated refers to the fact that it's very difficult to do something, that it requires a lot of effort. So actually, we'll be looking at both, mostly in the context of engineered systems. And well, multi-paradigm modeling is really philosophy is maybe not the right word, but it's a way of thinking about solving or dealing with complexity, solving complex problems. And it's all about modeling everything. Now, you might say, well, that's a bit much, model everything. You should read this as, whenever I have a problem, I should model each and every aspect of it explicitly. Yeah, and to put it to go a little bit more in detail, we should model every aspect of the problem at hand using the most appropriate views, because there may be multiple viewpoints, such as, for example, safety, energy use, and so forth. And architectures, we often deal with complexity by breaking down a problem into building blocks or combining building blocks. At the most appropriate levels of abstraction, we as humans are particularly good at working with levels of abstraction. We abstract from very complex systems, such as a city, Well, on a map, it's just a dot. We've abstracted that entire city to a dot because maybe on the map we just want to know, can you get from Delhi to Agra? And for that, I don't need to know the details of these very complex and complicated cities. Okay, using the most appropriate formalisms. Formalisms are modeling languages. And let's not forget, very often when we engineer systems, there are many, many stakeholders who all interact, many engineers who collaborate. And so there are very complex workflows. They from time to time need to sit together, exchange ideas. One may be waiting for the other. So these workflows are also quite important. And, but this is a bit outside the scope of this presentation. If we delve deeper as a computer scientist, it turns out that modeling language engineering, the engineering of new modeling languages, possibly domain specific, including model transformation, simulation, and so forth, are actual enablers. So we as computer scientists, software engineers, system engineers, we can actually make the above work if we work on modeling language engineering. Okay, but this talk is mostly about these dealing with complexity and looking at multiple views, multiple architectures, multiple levels of abstraction, and so forth. Now, in the meantime, you must be thinking, what is this model everything here? It looks like a glass. It is indeed a glass. It's a beer glass because, of course, I'm Belgian, and one of the main export products of Belgium, apart from chocolates and lace and carpets and so forth, is beer. And so this is a picture taken at one of our summer schools about domain-specific modeling, where we also have sessions, beer drinking sessions, but they are not independent from modeling, because actually we do practice what we preach. This is an example of a modeling tool, and in that modeling tool there is a model of the production process of beer. This was built by my former student and now colleague Joachim de Nil, who is a beer expert and who brews his own beer, and he actually built a model of the different stages. Of course, this is at a high level of abstraction. You can sort of figure out that there is a certain sequence with heating, with then getting the humidity out and so forth. But of course, behind this, there are models, typically differential equation models of these different biochemical processes that happen. So we do practice what we preach, and we do model everything explicitly. Okay, now it's all very well to talk about multi-paradigm modeling. Maybe we should first agree on what a model is. Well, there are a number of science philosophers, such as Herbert Stachowiak, a German researcher, who in his book about general model theory from 1973 says, well, a model is something which must satisfy the mapping feature. It must be based on an original. So I build a model of something. That's why I have that little figure above. It's a class diagram, which says that I may have a system or an artifact, and it can play two roles. It can play the role of the system under study, and it can also play the role of the model. So actually, it's really a modeling relationship between two artifacts. One is the model, and the other is the system under study. And of course, that's very relative, because I may have a little toy car, and that may be my system under study, and I build a differential equation model of its motion, and that's now the model of that toy car. But I could also say, no, the toy car is the model. It's now a physical artifact, which is a scale model of a full size car. So it's relative, right? And it's really not about, you can't say this is a model. You can only say it plays the role of a model. Now, that thing that plays a role of a model is based on an original. And of course, in engineering, very often that original is actually not there yet. Initially, we just have a set of requirements. And so that original, there's a little 4 here referring to an explanation which is off this page, refers to the fact that the original may still have to be built. There's also the notion of reduction. A model only reflects a relevant selection of an original's properties. And that's really, that word properties is very important. Why do we build a model? We build a model because we are interested in studying certain properties. For example, the trajectory of a car, maybe the fuel consumption of a car, maybe the safety of a car. All of these are properties of interest. We build a model instead of working with the original, doing an experiment with the original, to investigate these properties. And there's, of course, the pragmatic feature that a model needs to be usable in place of an original with respect to some purpose, and of course, with respect to some properties. We always have something in mind why we build this model. This is usually related to analyzing certain properties. Okay, here we see a little example of this. This is a very early model. It's a flight simulator. It's a flight simulator. You see there's a lot of manual intervention required, but it's basically the candidate pilot has to somehow adjust, make some adjustments to the rudder and so forth, based on whatever he notices as external perturbations. Okay, so that's maybe a starting point definition of a model. And from that point of view, this contraption here plays, which is made of some beer barrels, I guess, to make the link with the, or maybe it's in France, so it's probably wine barrels. To make the link with the earlier story. Okay, so of course nowadays training simulators look like this. This is at the Deutsche Luft- und Raumfahrt in Braunschweig in Germany, and of course inside it looks like this. This is not a real cockpit of an Airbus 320, but a training simulator cockpit. Okay, now maybe to jump ahead. If we build models, we have our, this is a model, in this case used for the purpose of training, a model of a real airplane. And of course, what is simulated is the environment, the environmental conditions, the flight dynamics of the plane. If we have a model, we are able to replace the real artifact. By the way, for the computer scientists among you, we know this in computer science. This is called Liskov substitutability, and the fact that if I have something of a subtype, I can substitute that, use it instead of something of the supertype. So it's all about substitutability, the using instead of. Now, what you see here is of course, quite a fast forward from what you saw with that French training simulator, flight simulator. This is something you can use today, partsim.com. It's a website, it's entirely web-based, and you can start building electrical circuits. Now, you might say, well, that's not that special, but you can also run these. You can simulate, and you can analyze the results, and it will actually plot the different electrical signals. And why is this important? With almost no threshold. It's web-based. I can just go to that website. I can start drawing these diagrams, push the button, and I can basically do what-if analysis. What if I replace this resistor by another resistor, and so forth. I can do what-if analysis in the virtual world before I ever build that real circuit. And maybe I will evaluate different alternatives. And finally, I decide this is the circuit I need for my purpose. Maybe it is a filter, an amplifier, or whatever. But what is interesting is that here we actually use specific parts from specific suppliers, Infineon, for example, and all the characteristics, basically a model of each of these components, which you can buy from a supplier, are actually in this system. So when I simulate, I'm really simulating what will happen if I build the real thing with these real components from these suppliers. And that, of course, explains who pays for the server on which this runs. And by the way, there's a simulator, which probably many of you know, called SPICE, behind this, running behind this. Well, who pays for this? Well, it's these companies. So this is a very interesting business model. where basically modeling simulation is offered as a service. And where is the money made? The money is made by, at the very end of evaluating your alternatives through simulation, pushing a button and pushing this button, BOM, which stands for Bill of Materials. It prints a bill of material. You give your credit card and your credit card number, and a while later you receive all these materials, all these components, and maybe even already a printed circuit board, and you just have to put them in there. So this is something we see more and more. You see this also in the production engineering world, where this step from requirements, what I want, then maybe trying out possible designs that satisfies these requirements, and finally realization, deployment and realization, that that whole process is becoming easier and easier, and more computer support is given for it. By the way, what I envision, and we also already start seeing this, is that the next step is that we no longer build our own designs. We give a number of requirements. For example, what is the if it's a filter, what is the profile, which frequency should be filtered out, and so forth, low pass, high pass filter. We give these specifications, and then the optimization, the building of variants of this model is also fully automated. So automatic matching between requirements and possible design. This is called DSE, design space exploration. And again, this becomes a service. And of course, what drives it is the fact that the suppliers pay for it. And I'll come back to this issue of suppliers later, because in engineering, this is a big deal. The fact that today we do no longer build, like in the early days of Ford, the Ford Model T was built from scratch. Ford built the metal, it made the rubber, it made everything from scratch, the paint. Nowadays, car manufacturers, for example, are mostly system integrators, and the components are built by so-called suppliers. So this is something that is typical for engineering, and that will keep coming back. So bear in mind that when I talk about multi-paradigm modeling for cyber-physical systems, that our ultimate goal is maybe to have an ecosystem in which complex cyber-physical systems can be built like this. Of course, here we are only in the electrical world. Of course, multi-paradigm modeling for cyber-physical systems will also deal with multi-physics systems, with heterogeneous systems, systems with multiple views on it, and so forth. Okay, now I haven't finished with my story about what is a model. Another way of looking at it is to say that again, I have two artifacts. One plays the role of the model, one plays the role of the system under study. Well, here we have our system of under study in the real world, and here we have our model in the virtual world. Now, this is a bit a restriction because in my figure here on the top, I could have a clay model of a car and then the real car. The clay model goes maybe into a wind tunnel. So it could be a physical artifact playing the role of a model of another physical artifact, or it could be a software artifact that is playing the role of a model for a physical artifact, or a software artifact for a software artifact, and so forth. There are many combinations. The essence is that we have a commuting diagram here, that we have some real world entity, like a car, and in a particular experimental context, we call it a system. We say we only look in this particular context, maybe temperature range, pressure range, and so forth, physical extent range. And in that context, and with a particular purpose in mind, that's also, of course, important, we are going to build a model. And this model may be a physical artifact, it may be a software artifact, it may be a differential equation, it may be a drawing, and hopefully we have some a priori knowledge to build on, probably given to us by scientists who have been studying the physical world for a while and actually have given us models to use. And then comes the main essence or the reason for doing modeling. I could do a real experiment within that context on my system. This gives me observed data from which I can calculate, compute, derive properties, such as what is the total energy used by my car to drive from A to B. But I could also do this with my model. I could do a virtual experiment through simulation typically, and that gives me simulation results. And if these two somehow correspond, we talk about a valid model. It is suited for replacing the real system. Okay. And of course, once we know that it's a valid model, we can start doing many, many experiments on a powerful computer. We do millions of experiments, maybe of small variations of the model, small designed variations. And each of these leads to a certain fitness, a certain level of quality of satisfying the requirements, instead of having to do a million experiments in the real world. And of course, we see an analogy with what used to happen by craftsmen before. They would build a chair, for example, and make it better and better by shaving off a bit and so forth. Well, we are now able to do this by making variations of our model, simulating, checking whether it is indeed better. And that way we can make a lot of progress. This is, of course, state of the practice now. No, this design space exploration is used in many engineering disciplines. And it is, of course, thanks to the fact that we can model, we can simulate on computers very efficiently. Okay. Now, as I said, the purpose really matters. And I already announced that multi-paradigm modeling will be about levels of abstraction, choosing the right formalism, the right notation, and so forth. And these choices will be driven by our purpose. And the purpose also includes the audience, because, well, it all depends. I can build a model. If I talk to a mathematician, the mathematician will probably like to see equations and formulas. If I talk to a contractor who is going to build my house, maybe they don't want to see mathematical formulas. What they want to see is a blueprint. They want to see some architectural drawing. And so it depends on the purpose. It depends on the audience also. Okay. Let's get back to this context, because I've put a box around it for good reason. There are many tools today that allow you to build models. There are languages which allow us to express our models in. Think of MATLAB, Simulink. We can write differential equations, and everything behind this, the computation, the numerical solution will all be done for us. We don't have to worry about this anymore. What we do have to worry about is that these models may actually not be valid universally. No, they're only valid in a certain context. Water boils at 100 degrees Celsius. That's a model. This is not a valid model universally, because we know if we take it to the top of Mount Everest, it will boil at 40 degrees Celsius. What is it related to? It's of course related to the ambient temperature, and ultimately we can figure out that there's a universal gas law, PV equals nRT, that there is a relationship between volume, pressure, and temperature. So maybe we should be careful. And most of you probably know Hooke's law, which gives for a spring, which gives a relationship between the force, which extends or compresses the spring on the one hand, and the deviation from the rest length x. There is a linear relationship according to Hooke's law, F equals minus kx. This is of course not true. It is only true up to a certain point. If I have very large forces or very large displacements, I no longer have a linear relationship. And at some point, I actually have two pieces of spring, because the spring will break and I will have two pieces. So obviously, having these models is useful, but we need to have a description of what their limits are. And of course, in industry, people know this. If you go to centuryspring.com, for example, there are, or if you order the catalog, the hundreds of pages of catalog, they sell lots and lots of different springs. You will notice that there is a catalog number, there is the size, there is the free length, which is if there's no force applied, what is its length in inches and millimeter. And there is this spring constant. This is the rate in Newton per millimeter. And then here, the suggested maximum deflection and the suggested maximum load. So basically, the maximum deflection, maximum X, the maximum load in Newton is the displacement is this way, the force is this way. So it basically gives us the proportionality limit with a bit to spare, basically, because they are promising us that if we buy a spring with a particular catalog number and we look up the suggested maximum deflection and maximum load and we stay within this, that it will obey that law. That is to say that if we simulate or we do the real experiment, we will get the same results. And this may seem obvious, but it turns out that many mistakes are made in engineering today because we reuse models, because it's so easy to use the model rather than do the real world experiment, but we start using these models outside their validity range. So this is a plea for not only modeling the normal behavior, but also modeling what the ranges are within which this is possible. And so suppliers, I will keep coming back to this a number of times in engineering. Many companies have suppliers who supply them with, for example, springs, and then they will combine them into a bigger product which they will sell. Okay, and so it's necessary to have some kind of frame which describes the context in which this is valid. And of course, let's not forget, the basis of all science is reproducibility and maybe even repeatability. And for that, we not only need to know what the experimental setup was, but also if I'm solving numerical equations with some numerical solver, I even need to know what the solver was, what the parameters were, like the step size of a numerical solver solving differential equations. And that is where engineering can still learn a lot from scientists, because scientists very often really describe in often still notebooks, describe the conditions under which they did their experiments so others can reproduce them. And this is something which is often a bit forgotten. And if we want to do fully automated design space exploration, we will have to model these experimental contexts too. Okay, now how to deal with complexity. Next step is, well, maybe if we want to study, for example, a power window. A power window is a window that goes up and down under the control of the human who pushes buttons. Well, that power window, and that example, I will use it a number of times because this is a power window we actually built. The mechanical part is maybe best modeled using some language, some notation. For example, here, this looks a bit like gears. Some notation which mechanical engineers understand and which has, of course, each of these blocks has behind it the appropriate equations. And rather than writing down the equations right away, maybe it makes sense to describe it in a block diagram like this. Is this the most appropriate formalism? I don't know, but it is certainly an appropriate formalism which is used by mechanical engineers to describe the different mechanical components. And we all know that there are, at least at the level of abstraction, of so-called lumped parameter models. We have gears, but we have all sorts of, here there's a worm gear. We have all sorts of rotational relationships, sliding relationships, and so forth. Okay, so most appropriate formalism. I have to mention the language Modelica because, as you can see, this is me here in my younger years. I was lucky enough to be part of the design team of a language called Modelica. Modelica is a language which allows you to describe a multi-physics physical system at an appropriate level. And why do I call it appropriate? It's multi-physics. You see here electrical components, mechanical control components, a PID control component. All of these are part of a single model. But what you see is I'm saying what my system looks like. And of course, it's originally a textual language with, for example, Ohm's law, R times I equals V. I'm not saying how to compute this. You could not write this in a normal programming language because you see on the left-hand side, there's no variable. There's an equation, there's a product. So I'm saying what the constitutive law is, how these current and voltage are related. I'm not saying how to compute them. If we use a programming language or somewhat in between the two, a causal, computationally causal language like Simulink, then I actually, you see these arrows here, I actually have to say what computation needs to happen. I have these two variables, and with that I can, and if I divide them, I can compute the third variable, then I can integrate and so forth. Well, variable or signal in this case. So as you can imagine, modeling at this level is easier to understand. And of course, the models are much more reusable because what I have here, there are actually three computationally causal versions of this, namely I equals V over R, V equals Ri, and R equals V over I. I would have to keep all of these around. Whereas if I keep it mathematical, these are called equation-based object-oriented languages. This makes your life a lot easier. So this was a little bit of publicity for the language Modelica. This has made engineers a lot more effective because they can focus on their design rather than on how to simulate the design. Okay. Actually, this is a nice figure by Akira Ohata from Toyota, who says, well, in the early days, we had Fortran, and we basically could execute numerical algorithms, but we had to come up with the numerical algorithms. Then later, we had libraries such as the numerical algorithms group, NAG library, the MATLAB, which put this in libraries. And so I don't need to care about my numerical algorithms anymore. I can just write down my simulation model like this here. The fact that this 1 over S is an integrator, I don't need to know that I could use a Runge-Kutta, fourth order adaptive step size. This is all taken care of by the underlying libraries, numerical libraries. But we could go higher. Actually, Simulink is actually a level higher because you could see I actually build a model by connecting building blocks. And so what Modelica and similar languages do, such as AMASIM by Siemens, is even these, I can now use mathematical equations, laws of physics. These are now my basic building blocks. Of course, I still need to know physics and I still need to analyze a problem domain, but you see everything in blue is done by the computer and everything in red is done by the human. So we can focus on the real interesting problems up here rather than having to delve too deep. Okay. So dealing with complexity, the story was, well, maybe if we use appropriate languages, notations, formalisms, our life will become easier. And by easier, I mean, we don't have to worry about all the blue part. We can focus on the red part. Okay. That's, by the way, the main argument for domain-specific languages. Now, I've mentioned it before. We have requirements and we have design. In engineering, at least, we have, for example, the desire to build a detached house, modern style, 2 floors, 2 bedrooms, 2 bathrooms, 1 garage, 1 cellar, and so forth. That's a set of requirements. By the way, here I have a product family because I actually allow many choices. So that's a family of choices. But if I make a particular choice, I've underlined a few of them here in blue, then I have requirements. And to satisfy these requirements, I will come up with a design. And by the way, this design is the floor plan I was mentioning earlier. One man's or one woman's design is the next one's requirement, of course, because from the point of view of the contractor, this is the requirements. And then the contractor will come up with a design and will make choices about which brick to use and so forth. But it's important to remember that in engineering, at least, at a very, very, very high level, we always turn requirements or a set of desired properties, in this case, they are structural properties, is turned into a design which is then deployed or realized. Yeah. Okay, this is important because, and you might think, what is this all of a sudden? This is Matteo Risoldi. This is a particular setup, and in particular here, this tracker Cosmic Rack, which detects cosmic particles, cosmic radiation, detects this. Matteo Risoldi was a PhD student with Didier Bouks, who you will hear later, PetriNet expert, developer of a language called CoOPN, Concurrent Object-Oriented PetriNets. A PetriNet-based, very powerful language. Well, Matteo's PhD was all about modeling this and then doing virtual experiments with them. And then finally, once he had a good model, he could analyze it, and he could also generate user interfaces and so forth and so forth. So now, there were requirements, there was a design, and then the requirements, he coded them as properties in an appropriate language. Now, it turns out that the language in which he described the design was something like this. And you can see this looks quite simple and is understandable by, for example, the people who operate this. Behind the scenes, of course, he would translate this to PetriNets, but the user would not see that. The user would just see this design. But to analyze properties of PetriNets, we use languages such as LTL, linear temporal logic, or CTL, and they look awful. You have to be an expert, a logician, to be able to understand these languages. So there is actually a mismatch between the design language and the property language. And that's something we always have to be careful about. Remember, NPM is all about using the most appropriate levels of abstraction, most appropriate formalisms. You could argue that this is a very appropriate language for design, but maybe LTL is an appropriate language for describing properties, but not for the faint of heart. The domain expert who is not a logician will probably have some trouble understanding this and writing this. So that's why what we say is you should, and I'm giving a very trivial example of an elevator here. If this is a model of an elevator, a domain-specific model, I have 3 floors. At every floor, I can push button, I want to go up or I want to go down. This one has been pushed here. There is an elevator that is currently at a particular floor, and in the elevator, I can push buttons to indicate where I want to go. Well, if I write the properties in the style of Matteo, I write the properties, well, I have to write them in LTL, and that's what it looks like. This is, of course, not most appropriate. You could, of course, argue, for me, this is not an appropriate design language, but at some level of abstraction, you see in in maybe 20 seconds, I explain to you what this means. So maybe this is quite appropriate, much better than if I gave you 100 lines, maybe of code or some discrete event simulation model. But what do we do with this property? Maybe we should match that same level. Of course, if I have this property and I express this in, say, Promela, and I use the spin model checker, I can check whether this design satisfies this property, which is actually very nice. This is what I want, especially because elevators should be safe and so forth. So I do want to check this, but this is probably not most appropriate. And maybe I can rewrite it in a more appropriate language, which is a combination of a temporal logic language and some for all floors. It goes over all the entities. It says basically for all floors with label O, after on the floor with label O, a button has been pressed. Eventually, that's a temporal part, in the fullness of time, on floor with label O, the elevator will arrive, which means, well, if I push a button, eventually, it doesn't say exactly when, but eventually the elevator will arrive, so there will be no starvation. Yeah? This is something I might want to know, whether the way my elevator system works satisfies this property. And it turns out that from a language engineering point of view, I'm going to look a little bit under the hood. From a language engineering point of view, we need a property language, we need a design language, we need a runtime language, which actually has a notion of current state. You see it highlighted here. And then, of course, we may want to see traces, snapshots over time, a series of snapshots of the state over time, which will probably be used as a way of showing, of giving counterexamples, because maybe if this property is not satisfied, typical model checkers will give us a counterexample, which I would actually like to see in my original domain-specific language, and maybe I would like to see even an animation, a simulation of what is wrong with my design. Of course, under the hood, there is a Promela, LTL, the Promela is the language, Spin is the model checker, and then some traces come out. Okay, how do we deal with complexity? Well, the obvious one is hierarchical decomposition or composition. And you will notice from time to time, you will see Julius Caesar here. Julius Caesar was a big fan of divide and rule. Well, we divide and rule. We split the problem into smaller problems, or we take small building blocks and we architecturally combine them. A perfect example is a computer chip with billions of elements, very simple elements, logic gates, which we build up in a hierarchical way. This has been one of the main ways in which engineers have built complex systems. Now, this is a little anecdote. A complex system such as a car, it turns out that Volkswagen had to recall 790,000 vehicles because if the rear brake light didn't work, all of a sudden you couldn't change your gears anymore. Luckily, it didn't block the brake, but still, that is not exactly what you want. And so according to the official communique, a faulty brake light could work in tandem with the shift interlock to immobilize the vehicle and require towing. Some of you may know what was the cause. It was intermittent, which makes it very hard to debug. And it seems very strange. The rear light is not working, and all of a sudden I can't change my gear. How are they related? Well, the answer is there are unexpected interactions between often heterogeneous components. And of course, we will only notice this when we study the system in full, because this here is a bit misleading. We could say we're doing so-called compositional reasoning. We know how the memory works. We know how the arithmetic and logic unit works and so forth. And then we put them together and we don't expect unexpected interactions, emergent behavior. Normally, we can keep this in check quite well, but sometimes we have problems due to the fact that in this case, this is the wiring harness of a car. This is typically around 1 or 2 kilometers long, and this is basically a bus on which all the signals are communicated. And of course, we can have bus contention. Typically, this is a CAN bus. This, by the way, is not only longer than 2 kilometers in the Volkswagen Phaeton, but it also means that there is a lot of copper in a car. But the problem is there are constrained resources. Namely, we want to communicate over this bus. And of course, every so many milliseconds, there is a message being sent by that faulty brake light. I'm broken, I'm broken. Normally in your console, in your display, a little light should come on. The problem is that also the shifting of gears, that signal is also sent over the bus. And if the priorities are not set right, there is an unanticipated interaction, namely that message of the gear shift never gets through to where it has to get through to. And we have a problem. So it's all very well to do this hierarchical composition, but we do have to be careful that it is truly compositional. And I'll come back to that later. Now, maybe we stay in the automotive world. with a sort of abstracted view of many, many engineered systems where you have a so-called physical plant, you have a physical system, you have an environment in which the system is supposed to work. And the environment, this is here the road surface, will of course determine how this plant moves. If I'm going uphill, I'll have to give more throttle than if I'm going downhill. Downhill, maybe I will have to brake a bit. So acceleration and deceleration will have to be changed to, for example, keep a constant speed. Where does that speed come from? Well, maybe with a cruise control, I have a reference speed being set by the environment. From the point of view of this system, I, as the driver who sets this reference velocity, is the environment. And we send this to the controller. The controller takes the reference speed and the current speed and somehow adjusts the throttle. Okay. Now, again, Julius Caesar pops up and says, well, you've done a nice hierarchical decomposition. There are three components: environment, physical plant, and controller. But of course, if I go just from a model of all of this all the way to building a physical plant and a controller that is realized on a board, a so-called ECU, a robust in a robust box on a maybe 8-bit microcontroller, there is still a huge distance, a huge gap between these two. And so that's why what we typically do is we build models of all these parts and we will simulate. And then before we actually deploy, for example, this controller onto a microcontroller, we will actually do some experiments to get confidence in the fact that our solution, our control algorithm, our deployed control algorithm is right. And maybe we won't put it in a real car yet, we will put it in a simulated car, but a very, very detailed simulation model which runs in real time. And that's why, for example, this T-Space Calexio is a hard real-time simulator for simulating vehicle dynamics. And that kind of simulation is called hardware in the loop simulation, Hill simulation. But there are other steps in between, and there Julius is again saying that, well, maybe this is model in the loop. We have the controller, the plant, the environment, and of course we communicate with the environment through sensors and actuators. But maybe we can go to different intermediate steps where either we replace the physical part by a simulation, but we use the real controller, or maybe we replace, we stick with a real car, but the controller we actually we simulate on, again, a very expensive and very fast simulation box, which using floating point arithmetic, whereas the deployed version will actually work with fixed point. So there is the splitting up of the problem, but now no longer in an architectural way, but in an going more and more towards a fully deployed or a fully realized system. And by the way, we will see this this sign appearing a few more times. There is no free lunch. Why not? Because of course, all these models that I build need to be consistent, because as modelers know, we should not fall in love with our model. A model is just a model. Maybe it is an invalid model and all the decisions we base on it are completely wrong. And I will only find out, of course, once my car is out there and things don't work. Okay, I will go over this very quickly. There are many of these intermediate layers. And of course, at the lowest layer, we are interested in the individual tasks running on the different ECUs, communicating over the bus, over this CAN bus. And you see here, some tasks are running, then they stop running, then they run again, and so forth. And the deployment problem, how do I take tasks and run them on a constrained platform, possibly distributed platform, is a difficult one. And it may mean that what you see here is our power window going up. There is an obstacle there, and the safety regulations tell us that we then have to back up, that we have to lower the power window. And at some point when the obstacle is removed, we can go up again. Well, this here, we may nicely prove that our controller actually does this. And then it turns out that due to some constraints at the level of my CAN bus and ECUs, that actually there's a little bit of delay, making my system unsafe. So there is some danger that we go from a nice model and we optimize everything, we go to a deployed or realized version, and it turns out that because of factors we did not take into account, namely the constraints on the bus and on the ECUs, that we actually do not get what we had simulated here. And this is called vertical consistency, that there is some inconsistency between what we see at the top level and at the bottom level. Okay, good. We're still looking at how to deal with complexity. Well, maybe we should look at most appropriate formalisms. There is an S here at the back. What we see here is our power window again. There's a controller, there's the mechanical part, there's an electrical part, and so forth. So there are these different parts, but they are, of course, described in the most appropriate languages. The mechanical part we already saw, this sim mechanics language, but maybe the control part we want to describe using automata. And that, of course, there is no free lunch. This will not be so obvious. If you ask me, what does it mean to combine an automaton with a differential equation? Well, I know automata, I know differential equations, but the combination of both is a hybrid model. It's a hybrid language. Well, this will be something that I will have to figure out. Right? And so it will add to the complexity. So although it makes it easier for the modeler, the control engineer uses his or her favorite formalism, the mechanical engineer uses his favorite formalism, and so forth. But then, yeah, what does the combination mean? So here we zoom in. There is the sim mechanics model of the mechanical part. And here is an automaton describing the modal behavior, including determining when there is an emergency and that we have to go down, which describes the controller. Okay, now how do we deal with this, with heterogeneity? Now, this is a very abstract view on it, but imagine here on the right that we have a hierarchical decomposition. We have a coupled model, or composition, decomposition, depending on the direction you go in. And we have three submodels and they are connected. They form a network. But there are two which are in formalism 1, the green formalism, and one which is in the formalism yellow. Well, for example, differential equation and automata, or maybe differential equation and bond graphs. Well, the answer is the only way we're going to figure out what they all mean is by translating all of them to a common language. For example, I could take bond graphs, I could take Forrester system dynamics and map all of them onto differential algebraic equations. So as long as we can find a common denominator and we can map it on it, then maybe we can make sense of what these red lines mean. And of course, we can do this in the continuous world. We can do this in the discrete event world. And you see state charts, finite state automata, Petri nets. This is a tricky one. It doesn't quite belong there because of non-determinism, but I'll say something more about that later. Now, of course, there is the great divide here. The moment we cross from this side to that side, the moment I go from a differential equation to a difference equation, we're doing an approximation. But okay, as long as we know what the error is that we make doing an approximation, we know what we're doing. It's an approximation, but maybe if our step size is small enough, we're close enough to the true solution. Now, this picture here, a formalism transformation graph, which basically charts all the possible transformations which preserve some properties. Well, one possibility is to say, well, I have this common formalism, which is here not shown as a dot, but as a line, which is trajectory, state trajectory, signals. And if I take a differential equation and the dashed or dotted green line is run a simulation, well, if I simulate it, it gives me a behavior trace. It gives me a signal. The same with automata, state charts, I simulate them, it gives me a behavior trace. So maybe the common denominator is the very, very lowest one, which is pieces of behavior trace, segments of signals, which will somehow be put together, which will somehow be combined. And actually at a higher level, it means that we will orchestrate simulators. And so we have a simulator for differential equations. We have a simulator for state charts. We have a system which has state charts and differential equations. Well, somehow we will let these simulators run in lockstep. We will orchestrate them. Okay, let me go a little bit more in detail in this, because this is today a very common way of solving problems. There is an architecture here with a model of the environment, a model of the controller, a model of the body. This is a prototype automated guided vehicle. It's something you often see in factories. They drive around and they carry a payload. Okay. Now, what you see is this is in MATLAB Simulink, this is in Overture, this is in Blensor. So it's very heterogeneous. And maybe the model of the body is delivered to me. Well, the body is going to be delivered to me by a supplier. And the supplier says, no way am I going to give you the model of the dynamics of this body, because this is my intellectual property. And it's up here to do full system analysis. Maybe you may remember somewhere up here, I said, where was it? Here. We need to do full system evaluation. Only then will we see that there are maybe unanticipated interactions. That's all very well. But what if your components come from suppliers who do not give you their models? Well, you could say, I'll build my own model. Well, that may take you a few years to reverse engineer that system and build a model. So maybe the supplier will be willing to give you a DLL, an SO, some compiled object, which is basically the model together with a simulator. So it's basically a building block, which in the simulation world at least behaves like the real thing, but you can't look inside. It's just binary, it's obfuscated, and so forth. So we're going to combine the subsystem simulators. We won't have direct access to the models, but we can play with them. Yeah, and this is called co-simulation. And what you basically do is I take the controller, I have my model of the controller, I have a solver, something that can bring it to life. That's my simulator. That's the simulation engine or solver. That's the model. And we do this for each of the components. And then, of course, there's how they are connected. Well, that connection topology is known to a so-called master or orchestrator. And then we have some kind of master algorithm which says, which determines when this simulator, the control simulator, can take a little step forward. This one can take a little step forward. This one can take a little step forward. By step forward, I mean, of course, step forward through time. This is the basis of what is called co-simulation. And this is, of course, needed when we have IP protection of our component models. Okay. We're still not at the end of our dealing with complexity. As I already mentioned, sometimes we have hybrid models where there is a bit of automaton which decides, this is a simplified version of deciding when to back off, when to no longer go up, but go down a bit when there is an obstacle. And there is a model of the dynamics, the opposite. This is basically a continuous model with a bit of automaton embedded. We could also have an automaton model with a bit of continuous embedded, like the bouncing ball. It depends a bit on whether the ball is flying, whether it is bouncing, whether it is stuck to the ground. We have different modes. So these are all examples of hybrid formalisms. So again, we use the most appropriate formalism. But in this case, it's actually a combination of two formalisms. It's automata, and it is, in this case, synchronous data flow, causal block diagrams, Simulink diagrams. Okay. And of course, it then becomes, if we now look under the hood, we will actually have to orchestrate our simulators. And so we will have to somehow combine the stepping of the discrete event, the automaton part, and the continuous time part. And of course, there's a whole theory behind how you can do this correctly. Because of course, in software, we can just do anything at all, but we are actually simulating real systems. So we must get correct results. And it gets interesting if we now say we have the physics of a train, but we have a track system, a system of railway tracks with lights, and the train may have to brake, accelerate, and so forth. And it's not really deterministic, that environment, when the lights go on and off. And I want to determine whether under all these possible combinations of lights going on and off, whether my system is still safe. That is to say, whether no two trains can be on the same segment at the same time, because that would denote a collision. And actually what you see here is that, like I mentioned here, we have to coordinate the simulator of the automata and the simulator of the differential equations. Here we are coordinating a simulator or an analyzer of Petri nets with one of differential equations. And you see, of course, that the behavior, the distance traveled as a function of time, is now branching. Well, if the light is green, the train keeps going at a constant speed. Of course, if the light is red, it has to decelerate, and it doesn't, the displacement does not increase. And you see, you get all these branching behaviors, you get this hybrid behavior. And of course, we can try to do model checking, namely figuring out of all these behaviors, are they all safe, or is there one of them that leads to an unsafe situation? Okay. We're still on the dealing with complexity, and this one has to do with levels of abstraction. We've already done it a few times, but here John McLeod, the founder of the Society for Computer Simulation, wanted, after the Second World War, build a heart-lung machine to replace, to use instead of the real heart and the real lungs. Of course, you can imagine he built one, not this one, something a little less modern. He built one and he wanted to test it, but it's rather hard to find humans who are alive and kicking, who will agree to shutting down their heart and their lungs and replacing it by his little heart-lung machine, just to see if it works. So he came up with a model of the human circulatory system, and he used hardware-in-the-loop simulation. He connected his device to a simulation of the human body. But of course, it ignored immunology. It ignored the human brain. It just said, well, the heart is a pump, and the lungs, they add oxygen, they clean the blood. And basically, all we need is a lump parameter model with the lungs, with the heart, and so forth in there. And basically, it's hydraulics, and then a little bit of what happens with oxygen and white blood cells. Okay, this model has been built, has been rebuilt in MATLAB Simulink, by the way. This was in 1966, but it is still a benchmark for simulation. It's called the FISB simulation model. This is obviously a very high level of abstraction, and it turns out more recently, more detailed models have been built of the heart. And this is an electrical analog. And of course, we can go even deeper. We can say, well, but actually, if blood travels through vessels, maybe there is some turbulence. Maybe I can build a 1D model, again, an electrical analog, because there is some resistance, there is some capacitance, some capability of storing, or we can build a 2D model, or we can build a 3D model. Yeah, depending on the properties of interest. So these are different levels of detail which allow us to answer different kinds of questions. So obviously, the 3D one will be necessary if I am interested in turbulent flow rather than just laminar flow. Okay, so what is the essence of abstraction? It is that if model 1 is an abstraction of model 2 with respect to some property, small p, in a set of properties, it means that if the abstraction, the more abstract model, satisfies p, it means that the more detailed model will also satisfy. So this means substitutability. I don't have to use the more detailed model with respect to the properties of interest. If I use the more abstract model, I do an analysis, it says the property is satisfied, for example, it's safe. Then if I did the more detailed study, it would also tell me it's safe. So basically, I can use M1 instead of M2. The opposite is called refinement. Now, abstraction lies in the eye of the beholder. Of course, Plato said beauty lies in the eye of the beholder. And it depends on the properties of interest. These are birds flocking. And obviously, it is in our eyes that we see a dolphin. There is no dolphin there, of course. But sometimes this is useful. sometimes we can see some property emerging like a flock. And instead of now computing, because we want to predict where the flock will end up in another 2 minutes, well, instead of doing that by computing the trajectory of each individual bird, maybe we can say, well, flocks, they sort of belong together. I look at their center, I look at how fast they're moving now, and I just extrapolate the speed, using the speed of the flock, I extrapolate the position of all these birds. And of course, this is computationally much easier. So sometimes this emergent behavior, we can do something with it that is useful from an engineering point of view. But to give you a nice example of emergent behavior, if this is an experiment called Boyd's, if I have 3 very simple behavior rules, saying that birds should not bump into each other, that birds will try to stick with the other birds, and if they look around and they see all the other birds flying north, well, then this bird will also fly north. These 3 rules, very, very simple rules, have, if you apply these, if you simulate this, you will see that always a V pattern will occur. This V is not encoded in the brains of these birds. This is something that emerges. So there is something there that sometimes we see something emerging, and maybe we can use this, like the flock abstraction I gave you before. And there are some examples of flocking. For example, these are little robots which have somehow found out how to connect, and they even connected and climbed out of the box. That is truly out of the box reasoning. Although this is, of course, emergent behavior. This was not programmed in these building blocks. Okay. Yes.
You have the 5 more minutes left.
Yes, I realize, and I think I will make it in 5 minutes. Maybe not the entire story, but I'm almost there. Thank you for this timeout. So, as I already mentioned, complex processes, workflows. When building this power window, we used 28 different modeling languages, which are actually charted here. That's such a formalism transformation graph relating them, and 50 different transformations and a very complex workflow. So in engineering, as I already mentioned in NPM, we have to model everything explicitly. Also the order in which we do things, when engineers will synchronize, and so forth. And so, by the way, this is an important part of this multi-paradigm, that we not only use multiple languages, formalisms, but that we also use multiple different workflows which need to be combined. Okay. And for example, an agile workflow is a workflow in which we take small bits of requirements and we process them. Okay, we also have multiple viewpoints. I can build a home entertainment system. I can look at the architecture. I can look at what kind of messages are being sent. I can look at the protocols, the communication protocols. So multi-view is also important. So we have different views of our power window, and there is actually an international standards which tells us how we can decompose into multiple viewpoints, and a view is then this governs a particular architectural view. But there is a problem. That is, multiple views are wonderful, again, to decompose the problem, but it leads to inconsistencies, because we may have different views on the same thing. And in these views, we build models. And I'm not going to go into the details, but if these different views are pertaining to the same properties, and in one view, I evaluate the property and it says true, and in another view, it says false, well, there is an inconsistency. So they either should both say true or both say false. Otherwise, we have an inconsistency. And of course, and this is where I go into accelerated mode, there are different ways in which we can deal with consistency. And there is horizontal consistency, there is vertical consistency. And we can deal with it by using contracts, by having agreements Some of you may know the Eiffel programming language and designed by contracts. But again, we need the right languages to build our contracts. Maybe that's again these things such as languages such as signal temporal logic. Remember, I had LTL, which was an appropriate language. So we can detect that there are inconsistencies and we can resolve them. Or we could also, I think I said it here, no? We could detect and then fix it, or we could try to avoid inconsistencies. That's actually what I meant with my story about contracts, to avoid inconsistencies. But of course, we want correctness of our system, but we also want to build our system as quickly as possible. So probably we want many engineers to work in parallel, but then maybe there will be inconsistencies, so we have to deal with them. Of course, we also want to work in teams, and maybe we want to have these brainstorm sessions, but for that we have to understand each other, and for that we may have to use our simulations. That's the top part here, but we may also have to build ontologies to actually come up with a common understanding, a common set of terms that at least among a certain group of people, there is a consensus about what they mean. And then, of course, we want to use both of these together. And I believe in the coming 2 days, we will actually hear about ontologies. Dominique, Blouin, and co have developed a very nice ontology of cyber physical systems, and I believe we will hear about that. Okay, and as I said, this talk was about dealing with complexity in cyber physical systems, and I gave a definition of cyber physical systems, but it's really about modeling everything explicitly at the most appropriate levels of abstraction, using multiple views, using architectures, and so forth and so forth. And many of these techniques actually lead to their own complexity, which we can again deal with, but it's really about model everything explicitly wherever possible. What I will not talk about, because that's a separate talk in its own right, is how do we now implement all of this? And that's where modeling language engineering, which is heavily based on computer science techniques and systems theory, will allow us to engineer modeling languages, the simulators for these modeling languages, the analyzers for these modeling languages, and so forth and so forth. So I will end my talk here, and if you have any questions, I'll be more than happy to answer them. Thank you for your stamina during my 1.5 hour talk.
Yeah, thank you, Hans. We got one questions from Slack, and in addition, I have some questions also. Uh, just 1 minute. Yeah. In the Slack, Rakshit Mittal from the BITS Goa, he had one question. So, how are these workflow formalized? And the next question is that, is there any standard practice which is used, that is learning from the past in the developing a workflow of the MPM in development of a particular product? So this is his questions. So
yes, okay, thank you. That's a very interesting question. And so the first one is about workflows. It turns out, of course, that there is a whole domain. Let me go back here. As you see here, this workflow has been drawn as an activity diagram. An activity diagram has activities, these round tangles, the rectangles with rounded corners, say, for example, model requirements, then model plant, and so forth. These are activities. There is a flow, a control flow, which says, well, first you have to model requirements, then it splits. And then in parallel, there is some modeling of the network, modeling of the environment, modeling of the plant, modeling of the control. And at some point, they are merged again. In addition to that, that's the control flow. We also see that some of these activities here in gray means that they are human activities, and the yellow ones are computer-based. These are basically translations, state charts to Petri nets, for example. And of course, what is nice about the activity diagram formalism, which may or may not be most appropriate to describe these workflows, it actually shows these rectangles here. They are the artifacts that are input to an activity. So you see there are some arrows going in and there are some arrows going out. So typically an activity, whether it is human or computer based, takes some input and produces some output. So this is a language to describe a workflow. Is this the most appropriate one? Is this the most common one? There are languages such as BPMN, the Business Process Modeling Notation. There are YAL, yet another workflow language. There are many, many workflow languages which can be used. This is just one example. The nice thing is it shows both the activities, it shows how there is synchronization, how there is parallelism, and it also shows how the artifacts flow through this. So there's, you could say there's both data flow and control flow. Now, I've said describe. We can use this to describe a particular workflow that today happens in a company. And I may then use it as a starting point to optimize it. This is what we do when we start new projects with companies. We listen to them and we make we chart basically what their processes are. And also, of course, you may notice that each of these boxes, these artifacts, is written, is an artifact in some language, and these languages are charted here. This is just a map of all the languages that are used: PetriNet, state charts, plant domain-specific language, SysML requirements diagram, CTL, and so forth. So it turns out that this is good for describing what happens. You could also turn it around and you could say, no, I'm going to use this to prescribe what must happen. And you can use it as input to a system, which then, for example, sends emails to individual engineers saying you must now start with that tool to work on this task and so forth. And this is, of course, this exists. There is product lifecycle management. There are commercial tools for PLM, for product lifecycle management. But now, thank you for your question about learning. This is, of course, the hot topic. If I do business process modeling or workflow modeling, it's somehow I describe what happens. The next step, and the guru in this domain is Will van der Aalst, now in Aachen. He basically cleaned up this entire field of business process modeling. He started with modeling languages, including this language YAL, which he developed. He described it. And then he had a lot of projects with hospitals, for example, where there is a requirement that particular procedures are followed. So what he did was, instead of just using a model and maybe simulating it and providing or generating behavior traces, he actually started from behavior traces as you observe them in the hospital, and then a workflow as it should be executed in the hospital, and then he would detect anomalies. Okay, but that's only step 2. Step 3 is the state of the art now, and the state of the practice is I give you a trace of what happens in a company, and you somehow, and this sounds a bit like machine learning or AI or pattern recognition, you actually give a model of the workflows. And this is called process mining, that we actually try to basically from the data, we actually extract from the behavior traces, we extract the process models. And this can give us lots of insights, and of course, which will form the basis of then future optimizations. And so there's this entire spectrum, but of course, the way this is done is that is going from data to model is by looking for certain patterns that reoccur, and these patterns are then translated to patterns in the workflow language. I hope this answers your question about both the workflow and about the learning.
Yeah, I think so, because there is no messages coming in the Slack. So
Good.
yeah. So thanks, Professor Hans, for a nice keynote on the MPM for CPS. I missed it during the Paris time because yeah, last day I did not attend the meeting. Anyway, so now one of interesting sessions. It's basically the sub-sessions will be going on. That is the dialogue. I'd like to introduce one of the panelists, Professor Dipankar Sharkar. I think he's there. Professor Sharkar? Yeah. Sir, your audio, your mic is muted.
Sure. Yeah. Hello. Hello, everybody. Yes.
Hi. So, so this is basically one of the panel discussions on the Petrinet related works. I'd like to introduce Professor Sharkar. Professor Sharkar was working in the IIT Kharagpur, the Computer Science and Engineering Department. The specialization is mainly the formal verifications and symbolic logic. And eventually, I was the one of the PhD students who was working under him. I'm the only one person, I hope, who is working on the Petrinet
Yeah.
under you.
That's
So the topic of this discussion is how much Petrinet is relevant as a modeling paradigm. So I would like to go first, Professor Hans, and then Professor DS. So
Thank you. The relevance, of course, is also in the eye of the beholder, no? And of course, as in every community, if you have a hammer, everything is a nail. So I'm preaching a bit the fact that we should not stick to one formalism, but then again, in the Petrinets community, there are many variants of Petrinets, each with their own expressiveness. So that is already multi-formalism. Yeah. Now, I would say that the essence of, well, maybe first something about paradigm. Can we talk about the Petrinet paradigm? My title was multi-paradigm modeling, but I didn't explain what a paradigm was. That is, maybe you may have noticed this small detail. I didn't really say what a paradigm was. Now, the main message was you have to model everything explicitly using the most appropriate and so forth. Of course, when it comes down to formalisms, it's clear. We need to use the most appropriate formalism. And maybe for certain problems, when I want to study the continuous behavior of a physical system, I'm going to use the laws of physics, and I'm probably going to end up with a set of differential equations, partial differential equations or the differential equations. So in that case, probably for the properties of interest, namely the detailed physical behavior, the evolution of the position, and so forth of time, Petrinets are not most appropriate. On the other hand, maybe if I want to study that system at a higher level of abstraction, and I'm interested in, I once met a professor from Manchester who had worked with the candy factory, what is it called? Cadbury. And they had a machine that built wrappers for chocolates. And instead of taking a chocolate and wrapping it, they actually shot the chocolate at a wrapper. And that way it wrapped itself. Now you can imagine this is like a machine gun. And the control algorithm of this needed to be analyzed, whether it was safe or not. And that he did with Petrinets. So again, this is a physical system, but at some level of abstraction, Petrinets are the most appropriate level of abstraction. And I would say whenever there is a notion of concurrency, whenever there is a notion of synchronization, whenever there is a notion of non-determinism, that probably, and if it's somewhat discrete, I would immediately think of Petrinets, and then I would, of course, think of the matching kind of liveness, safety, whatever kind of properties that I can analyze. So is it a paradigm? It's definitely a formalism or a family of formalisms. To me, it becomes a paradigm if it satisfies certain properties at the language level and at the workflow level. Like I would say that we could talk about the agile paradigm. Yeah? That's only about workflow. And there are many, many workflows that are all agile because they are cyclic, they have short sprints, they always pick off a little bit of the requirements, and then they process them, and you have a working artifact, and so forth, and so forth. So that I would call a paradigm. In the case of Petri nets, I would say there is definitely a paradigm there which is discrete, which is about synchronization, concurrency, non-determinism, and so forth. I would call that a paradigm. Is that the Petri net paradigm? Well, it's definitely very well satisfied by Petri nets, by the formalism Petri net. Is it a paradigm? I don't know. So that's maybe a weird answer to your question. Is it relevant? I think Petri nets are extremely relevant. Whether I would call Petri nets a paradigm, what's in the name? Actually, the whole cost action, as is often the case, we spent, I think, 4 years trying to figure out. So the title of the project is Multi-Paradigm Modeling for Cyber-Physical Systems. We spent 4 years trying to figure out what multi-paradigm means. And I don't think we know yet. So, but is Petri nets relevant? Yes. I think you're still muted.
Yeah, Professor Sharkar, what is your viewpoint? So please share how you looks the Petri net as a model in programming language point of view.
Yeah, I think, okay. I mostly agree with whatever little exposure we had. We means yourself, Professor Soumyadip Bandyopadhyay, and myself, we two. We had a co-guide, or I mean, Professor Soumyadip Bandyopadhyay had a co-guide also, Professor Chittaranjan Mondal. And as Professor Hans has rightly pointed out, I mean, it went like this during our work that we just thought, we chanced upon a particular kind of model which is based on Petri net. The authors of that model called it Press Plus model. So essentially, that is what led us to work with Petri net as modeling paradigm for analysis of programs, so far as equivalence checking, translation validation is concerned. But unfortunately, what our experience, of course, the work we carried on to its logical conclusion to the best of our ability. But unfortunately, my feeling was that Petri net was becoming a bit of a burden when it came to capturing programs with so much of computations involved, and the model became quite heavy. The overhead became quite a lot. However, of course, from our student days, from mid 70s or even early 70s, I suppose, Petri nets have been finding use very effectively in, as Professor Hans has pointed out, in modeling concurrency, non-determinism, and so on and so forth, especially in the context of operating system. So that's what my feeling is, that we'll have to judiciously choose the area of application where, because if we commit ourselves to a modeling paradigm, especially when we have such a huge amount of experience as research community across the globe, it will not be wise to fall for a particular model irrespective of its area of application. We should judiciously choose, and we should also, models at different levels of analysis. It will require different kinds of modeling paradigm, and depending upon the abstraction that we can resort to without losing the significance of the properties that we are trying to establish or examine, uh, Petri nets will surely have their relevance, but it should be judiciously applied. Definitely, that's the most important thing, that whatever little experience that we could gather, that's what my feeling is. And of course, Petri nets, with colored Petri nets, I mean, they have plenty of scope so far as modeling goes, but to what extent they will lend themselves to analysis, that's a big question that one has to somehow foresee it before plunging into or committing oneself to a particular kind of model like Petri nets. So that's what I fully agree with Professor Hans, that I mean, wherever certain issues are involved, and those issues are already quite well identified, definitely Petri nets are still relevant, in my opinion. Yeah, but we should not overcommit ourselves to a particular kind of modeling paradigm. Yeah, that's all I had to say about it.
Thank you, sir.
Yes.
Now my another point of interest is, so both of you are basically in the formal methods, and somehow you are doing the verification. So from these discussions, what mm, the current point is that, uh, what is the future of the formal verifications in this era, where the era of machine learning, so the era of the data sciences comes into the picture? uh, in broader sense, what is the role of the formal methods, the formal verification in the future? So does it have any future, or the entire things will be shifted to the AI related stuffs? So yeah. Mute, sir, mute.
Yeah, let Professor Hans speak first, because yeah.
Okay. Well, I have strong opinions about this. I think it's all about the most appropriate. We should not switch to doing everything with machine learning, deep learning. We should not throw away the knowledge of physics we have, of solving differential equations. We should not throw our knowledge of model checking and so forth. That's where the multi paradigm comes from. Use whatever is most appropriate. And as was just said, choose judiciously. And that's where, and I think in education, this is a very big task for us as educators at universities, is to make clear what is the most appropriate level of abstraction, what is the most appropriate formalism, and the supporting tools for a particular problem. And this is the art of modeling. Yeah? And we will use whatever is most appropriate. Yeah? And sometimes it will be indeed some form of machine learning, but very often model checking, because of course, when we talk about formal methods, there's a huge spectrum. We have proof assistance, where we actually do proof, mathematical proof, but with some assistance by some tool. We have model checking, where we have a particular system with a particular initial condition, and then a lot of branching behaviors. And over all of these behaviors, we want to check that certain properties hold. That is not the same as what you do with formal proofs, which are even more general. And the other extreme is simulation, where I have one initial condition and I simulate one single trajectory. So there's this whole spectrum. And of course, wherever we can, if it is possible to find a level of abstraction where I can formulate a problem, like in the form of a Petri net, or in one of the Petri net languages, in such a way that I can capture all relevant behaviors, then I can do my model checking and I can check whether deadlock will occur and so forth. But of course, remember, it has to be a proper abstraction with respect to the properties of interest, so that if it says no deadlock occurs, my analysis, my Petri net analysis, and I then go to the real system, well, deadlock should also not occur. So it's this, my plea is for use whatever is most appropriate. So I don't think they're in competition. It just means that there is a wide spectrum of problems for which, in particular, model checking is very useful. But we have to know what the boundaries are. And of course, we're pushing the boundaries. When BDDs, binary decision diagrams, were invented, that really pushed the boundaries of the state space that we could explore in model checking. So there are these boundaries being pushed. And of course, the central memory of computers is growing, but everything has its applicability range. And the idea behind multi-paradigm modeling is use whatever is most appropriate, but we have to be aware of these limitations. So that is my my answer, maybe not entirely to the question, but use whatever is most appropriate.
Yeah, okay. Thank you, Hans. Professor Shorty?
Yeah, I don't have much more to add beyond what Professor Hans has said, because that's the wisdom that one acquires. That essentially, surely theory proving is a very heavy activity. I mean, formal verification in general, and therefore, unless you have modularized, you have through granularity. See, basically it's a kind of top-down approach, and people would like to get start from holistic. I mean, starting with a holistic approach, one will take a top-down approach, and then at some level, definitely problems will come out to be tractable and manageable enough, and where there will be relevance. That is very important. It is relevant to prove properties, because they are essentially these building blocks. They will finally their soundness will finally get reflected in the hierarchy up. So naturally, it is definitely relevant, and I don't think any kinds of tools and knowledge that's available that we should use when it comes to building a complex system, and we should not force ourselves to the mechanism of analysis right from the beginning. Definitely, we should be conscious about the applicability, the limitations, and but my experience, to the extent I have found that at some level of granularity, at some level of modularity, definitely problems reduce to uh, the tractable level, where formal verification will play a very important role, and that will definitely cut an ice with the users of the system, or whoever the engineers, or basically the people who would be benefited by using this system. So we cannot take a straightforward approach. We need not be very. We need not draw a very gloomy picture for formal verification. Definitely, they have their worth, provided we keep applying them at a certain level. That's Professor Hans has pointed out. Definitely, yes.
Thank you, sir. So I think if we continue these discussions, it will be the long time, but we have very harsh time. We have to complete this session soon. So
If I may, because of the comments made just now, make me realize that maybe some more overarching statement could be made. If I could have 1 more minute for that, is that okay?
Yeah, please go ahead, because we have probably time.
Yeah. Okay. So
Yeah.
it's about usability. When are formal methods usable? And I think we have to be careful that remember my little example of the elevator. It's obvious that modeling that elevator system with Petri nets, this is what I give as an assignment to my students, and modeling in LTL the properties of interest, that's also what I give as an assignment, and then doing the model checking, you can give this as an assignment to computer scientists. But maybe for industrial adoption of formal methods, you need that extra level on top. You need a level where you use domain-specific notations, and where we as computer scientists can provide then translations to basically what I would call the assembly level. Like in programming languages, you translate down to machine level, and this is done by a compiler. So maybe one aspect of usability is that it is cognitively usable, that it is easy to understand. And maybe it was mentioned before, Petri nets are heavy notations. And maybe I have 1 million places and 500,000 transitions and so forth, and 2 million arcs. Maybe that's actually not a problem as long as I don't have to look at it and build it myself. Maybe there is some higher level language which I can use, and I use that as an underlying assembly language. And then whereas the assembly language or machine language is executed by a data part by a particular hardware, well, in our case, that assembly language PetriNet model and then the LTL formula or CTL formula, that is used by a model checker to come with results. Of course, then the backward translation of the counterexample to something I can understand as an engineer is of course an issue. That's point one of usability. Point two is scalability. That's already been mentioned. But let's remember that at least in engineering, we are very good at saying, well, I really want to prove using model checking, for example, that deadlock cannot occur. So what am I going to do? I'm going to compromise. I'm going to design my system. And this was also mentioned earlier about this modularity. I'm going to design my system, maybe not optimally, not cost optimally, but in such a modular way that it becomes amenable to analysis through model checking. So by construction, we design our engineered systems in such a way that they can be checked. And this is what we do in electrical circuits also. We make them independent, and we have done some impedance matching and so forth. So we actually introduce a bit of overhead, but then maybe to put it in the context of model checking, maybe we get some compositional model checking maybe. And so I think there are this scalability issue is often, well, we can deal with the scalability issue, even although at the first glance it's not scalable. Well, then we just say we'll build our system differently, and it may not be cost optimal, but at least it's verifiable. And I think this is something we should not overlook, that we as engineers, we build things in a certain way to make them more maintainable, to make them more analyzable, to make them more like in assembly systems, to make them easier to assemble and so forth. Okay, so that was a few more remarks.
Yeah.
Thank you.
Thank you, Hans, and thank you, Professor Shorter. So it's a very nice discussions. So we just end this session, that is the sub-sessions, that is the dialogue sessions now. Now, in the next talk is basically will be given by Professor Sunil Bhand.
So Rakshit, can you allow me to come in? I'm not able to operate my video. Let's see what to do. Yeah, that's fine.
So, Dr. Soumyadip, allow me, when should I start?
Yeah, so just 1 minute, sir. I just give you the introduction first, and then you just start.
Okay, thank you.
Okay. So Professor Sunil Bhatt is a Dean of SRCD in Pilani, and carried out his doctoral research on industry affluent analysis with reference to heavy metal specification in adequate environment and sediments in 1996. He worked as a postdoctoral research associate at Department of Pure and Applied Biochemistry in Lund University, Sweden from 2001 to 2002. He has received significant funding and executed various national and international projects from CSI in New Delhi, the Swedish Research Council, Indian Council of Agriculture, Rakshit, you just share my screen.
Hello. Yes, sir.
Yeah.
What should I do now?
No. Just stop sharing.
I would also like to talk a little bit about Professor Bhand.
So, and basically the World Bank, USA, Department of Science and Technology, etc. So, in this seminar, he will be talking about the systems on the BioCPS. So he's he's the keynote speaker in this track. So I just hand over my the mic to Professor Bhand.
So can you hear? Can I say a little bit about Professor Bhand? Yeah. So he is in the Goa campus, and we all are working together for betterment of the BITS Pilani overall, and he is kind of guiding us. And recently we could make a project of the DST project on the BioCPS. So I think he will little bit touch on that, which is the upcoming thing from BITS Pilani. And I'm sure that probably he will cover a bit of that. And if not, we will definitely discuss on this issue at the end, maybe tomorrow sometimes. And thanks, Professor Bhand, for coming and giving the talk. Thank you.
Thank you, Soumyadip. Thank you, Professor Sumit. Good afternoon to all of you from Goa, India. The weather is quite nice, so hope you have the same there. So Soumyadip, may I share my presentation, or is that visible? I have tried to share it. Is that visible too?
Yes, sir. You can just share your screen. So
I have shared my screen already.
Sir, can you please do it again?
Okay. All right, I have to do it again. No problem. And then. Yeah, is that coming now? Please confirm, Rakshit.
Yes, sir. Yes, sir.
Okay, can I go ahead if it is all right?
Yes.
Okay, so yeah, good afternoon to everyone, and I am Sunil. I lead a biosensor group at Goa. Joined BITS in 2002 and then moved to Goa 2005. My talk, as Professor Samit said, I will cover a little brief touch upon this new project, Bio Cyber Physical System Technology Innovation Hub. And I want to take a simple example of our work and then try to share where our opportunity for collaboration might emerge, because I am more an experimental chemist now, started with a theoretical chemist, high resolution molecular spectroscopy, then in between, and then turned to biosensor. So this is my outline of my presentation. Ideally, a bit about BioCPS Hub, then what are the focus areas in our hub we are going to initially start. We will expand it further, and then I'm going to take 2 or 3 examples on enzyme thermistor or thermal biosensor, how they could be potential candidate for a good biocyber physical system, and also the capacity of sensors or biosensor which we have developed in our group. That's what I thought of for a 30-minute talk, so that people get a feel of what is the big picture and what is the small picture together. So talking about this BioCPS hub, the idea is to develop a technology innovation hub, offering a common platform to nurture interdisciplinary and collaborative research. Keeping that focus, this will be supported by a vibrant innovation ecosystem where industry and academia can interact very closely and try to emerge with new knowledge and new science. I was quite happy to hear the talks of Professor Hans talking about also subsequently that we should not forget science, and we keep both, maybe the computing part, the AI part together with that. So the purpose here is we intend to utilize or integrate and see the overlap how the AI and IoT and computer science can integrate for solving various societal problems like human diseases in biology. Professor Samit is an expert. Then bring in chemical engineering, biochemical engineering, which is also part of bioengineering today. Work on biopharmaceuticals, biosimilars, the antibody-based, treatment of biomaterials using biomaterials, and also make the devices. So the hub in principle is going to have a fabrication facility. It is going to have a knowledge generation facility in bio and pharmaceutical area. It will have also the IoT field where the products which are coming out from the devices through integration of biomarkers will be integrated into IoT systems, and then demonstrate the sensor network and try to same time also have some model system where the computation power, the biological computation power can be exploited and integrated into various aspects. So that's major or broad scope of the hub. So in principle, three components, as I shared, the discovery approach in the biomolecules will be having a next generation sequencing instrument, quite expensive and useful, like about 1.5 million euros, wherein the biologists or the bioinformatics people will start working on identifying various novel sequences or different kind of biomarkers, and try to come out with those which can be synthesized using the NGS, and then go back and develop testing platforms. I will share one or two which we have developed in our lab, and try to demonstrate how these biomarkers become useful in the diagnostics of diseases, monitoring human health, and try to showcase at a community level broadly, if we are successful, of course, so that we can focus on ultimately smart city goals like food supply chain, food traceability, safe drinking water, and point of care health monitoring system. And obviously there is an IoT and a team from the computer science and also from the communication systems, which will ideally this is where an opportunity where Telecom Paris could be discussing this, how we can probably work together on this aspect, making wireless communication, smart system. I was listening to the lecture by Professor Hans. I'm a chemistry person, but I was quite, intrigued by the ideas on how the differential equations could become useful and so on. So that's another opportunity, how we bring it to the mobile devices. And also, obviously, a lot of data will be generated in terms of bioinformatics or even the data management when we deploy the sensor network for healthcare monitoring, for instance. So develop data-driven strategies wherein we physically build the sensor, integrate them, and maybe model and then find out, maybe, I do not know, I'm an expert. I'm not an expert, so I just feel that something interesting can come out which could really impact the society in a larger scale, particularly in a setting where India is densely populated, heterogeneous population, the medical facilities are at different scales, the physical infrastructure is entirely different in rural and urban settings. So with that goal, we have to have certain deliverables end of the day, because it's a very targeted technology innovation hub. While research and basic research is one component, there's a very high demand by the government of India to be at least demonstrate some success stories, at least some model systems where you say, okay, some novel biomolecules we are able to discover or maybe deliver. Some practical devices have been at least prototyped, modeled at the field condition, and try to see whether they really work or we are still in the laboratory, and also create startups and entrepreneurs. And we have possibility for a new area of BioCPS where we'll have the incubation facility where students can work. So there's a lot of opportunity for students to involve and demonstrate some technology transfer, because we have certain leads where we would like to take it forward quickly, and there are some leads which will start from the bottom wherein new knowledge has to be generated. So these are primarily the goals on various levels of faculty and students and industry and startups and MSME. So this is what some of the deliverables that we are expected to end of the day. We are going to create a reasonably, not a nano-electronic facility, but per se a small fabrication for low-cost devices, using thin film devices, using the printed electronic devices, and so on. So which startups could use, prepare some new design, and that's where I think design engineering probably can participate. Again, it's all my anticipation, but there are experts from BITS who could talk to you in a better way, like Dr. Soumyadip and others. So we would like to have industry connect in prototyping and seeing whether they are worth evaluating subsequently. Obviously, if we reach that stage. So that's the overall, about the BioCPS hub. These are some of the existing collaboration. Now we'll be adding Telecom France also in this list. But you could see we have extensive collaboration worldwide today, right from US to UK to Europe, also with France. I have mentioned only one, but we have at least 2 or 3 now active collaborations and so on. So I believe so that with our this opportunity, we will be able to carve out a couple of channels where probably knowledge sharing and knowledge exchange could happen effectively. So this was about the BioCPS. Allow me next 10 or 15 minutes just to share with you through my research how I foresee and how I have been working last 20 years in the area of biosensors, how they could probably have some pathway integrate with this philosophy of cyber physical systems. Let me share those few examples. So this is just a quick overview for those, some of you are already knowing perhaps. I heard impedance quite a few times, was excited to talk about that later on. So ideally biosensor as a device, they are constituting biological recognition element, as you see on the left side, the analyte, which could be a chemical substance, a gas, could be a liquid, or could be other sample from biological, could be urine sample or could be food and so on. And you have various biological recognition elements primarily coupled on your transducer. And that's what you people are expert at, that if you have a transducer, maybe a pH or maybe a photomultiplier tube or maybe a microchip, for instance, or it could be optical, could be electrochemical and so on. And you can primarily then expose this biological interaction of a chemical substance or a biological substance and try to quantify that interaction. That's fundamental principle for some of us just to relook at. And then the data processing, I also heard artificial neural network and so on. We also have collaborated with the French group on ANN sometime back on the diagnostics. I think that has some promise, I believe, from those results. So with that basic information on biosensor, I'm going to share an example and few scenarios how we have been, visualizing this biosensor using, very basic property of, exothermic or endothermic biochemical reaction. So many of the biocatalysts, when they react with the, reactant, they will produce heat, and that's the very simple principle of thermodynamics. This work I started collaborating with the Swedish group in 2000. Now almost 20 years complete. 3 projects completed with them continuously. But this is something which they came up with the enzyme thermistor, wherein primarily you try to focus around measuring the heat resulting from the biochemical reaction inside a bioreactor in a specific setting, which I have tried to describe here. While you have the first generation transducer with the Wheatstone bridge on the upper picture, but primarily you have a pump and a flow system where your biological fluid or your buffer is continuously flowing. I'm describing a situation where the bioprocess industry is extensively using, particularly the fermentation industry. I was visiting Rome last year and saw some of the vineyard, how they are using sensors, some of such sensors today, not thermal, but other type to check the wine quality and check the beer quality and so on. And this could be interesting that in a flow system, how the immobilized enzymes are being used. So what you see here is the insulated, a chamber inside which in the brick red color, there is an immobilized biocatalyst. And when you pass your sample to the injector, you primarily, I saw this could be a lab view programming or also Simulink programming. I think, pardon me if I have misunderstood, but primarily this is something which is now already automated to my knowledge in the industry. But what is more interesting part is if you have sensors, you could primarily design. So this is one right side schematic where we took, porous glass, control pore glass, which is extensively used in biomedical industry. You have nanopore size holes inside which we mobilized, biomolecules in the red color. pack it into this blue column, and then when the heat is liberated, the thermistor is sensing, and it goes to recorder, and nowadays it is on mobile phone, not anymore on the chart recorder. So with that basic background of the instrumental setup, this is one setup which we are able to develop several now applications for food industry, for glucose monitoring, for food syrup like fructose, where you call artificial sugar, for instance. So you want to monitor this. So we tried this setup also in a factory in Sweden, south of Sweden in Skåne, and try to see does it work well. It gave good result. But also now I have developed this setup in India, wherein we demonstrated for urea analysis. I'm taking a case study now, subsequent to this slide, that urea is an adulterant. I think could be a new word for France or for Europe, wherein if you are aware of adulteration, means something people add over and above and existing in a milk sample to enhance some of the qualities or parameters. For example, you try to see amine group, which is an indicator in a good quality milk, but urea is also NH2 group, amine group. So people add, instead of taking a natural route, they use a chemical adulteration, and that has become a problem because urea can cause cancer and also kidney diseases. So that has become important in the milk supply chain. I am going to take this as a case study, as an opportunity for you to think how can you come up with such ideas, not necessarily on this line, maybe other line also. So we developed a urea sensor which could detect up to 200 millimolar of urea, and primarily you want up to 100 millimolar in milk to be detected, whether it is good or bad. So objective was to have sensor which could, ideally have different scenarios, that one where the milk is being collected after from the day coming to the milk processing plant. So there are various collection centers. You also have dairies where animals are directly kept there for milk production. You also have urea in urine, a medical biomedical marker. So what we did was we had now the new thermistor setup, and we replaced the data and integrated the data recording directly into the mobile phone. Objective was very simple. In India, when you have a bad sample, nobody will tell you there is a large chance of manipulation of the data. So the intent was to make the machine independent of the operator. If you had an automated machine and the data can go directly to the various end users. The end user could be a regulator who wants to know that this is something going on wrong in the processing plant, a consumer who wants to know that in my milk there is something wrong, and also this could be a pathological laboratory which is using clinical samples. So we have actually demonstrated this in 2015. It was a student who just passed out undergraduate degree and did the mobile programming on open Android platform, and tried to show that you can actually have signal directly passed on to end users, but this was with one sensor. So ideally these were the scenarios we thought of: milk collection center, agricultural field for soil urea content, clinical analysis I told, milk quality check for consumer or at individual level, and also the data analysis of the records collected for keeping track on the supply chain or the food traceability. I think that's very important today in Europe and also in India. And that's where we are working currently on those models. So this is one such example wherein we also made a decision support system. This was done by a computer science student in my lab, and tried to show that if there are the safe levels, you have the green signal on your mobile, and if it is unsafe and crossing the limits, you immediately have an alarm, and it gives an alarm. So today, I was talking to my French collaborator in Perpignan, and they said, yeah, every time you have these grapes being collected in the vineyard, and then you have to go for testing and see whether there are any toxins present. And unless you have that certification, you cannot process for the winemaking or other products. So this could also be interesting that if there is something going wrong in the wine or in beer or in milk, we could have this kind of a sensor network. We have not done sensor network so far, but this could be an opportunity to train maybe a network and so on. So this was an alarm system developed. These are real sample analysis results shared on the mobile. So the moment there is a wrong signal or a bad sample crossing the limits, so blue is the cutoff limit for urea, immediately an alarm and SMS goes to the user. I think this could be something useful that before somebody consumes the food product, if he or she gets the result. Unfortunately, today there are many situations where patient dies of COVID and the RT-PCR results comes after the death. There are in India situations like that. So there are need for healthcare diagnostics also, not just this urea sample. So this is one example that this could be useful if you make the system automated, free from corruption and manhandling. Would be very important for. So this was a big project funded by Ministry of Agriculture, wherein we demonstrated these samples. We filed almost 12 patents, 3-4 are granted now. We are working on those commercialization. That's why Hub probably can help us develop those products. This is another platform where we work with the Swedish group on the impedance-based, sensing. Swedish group was more on the material science, but this was the chip design, an impediometric chip developed for the mycotoxin analysis in milk. We also tested on the Cadbury and meeting the Swiss standards for the chocolates. I heard somebody mentioning Cadbury here, so I thought there's some overlap, so to say, on the lighter note. But in principle, we developed a 2-wire-based electrode, biofunctionalize it, and make it bioimpedance measurement. That's the basic concept, not very new, but we made some innovation. We have now an international patent granted on the chip, biochip. Also, we have an Indian patent under consideration at the moment. So idea is also to enhance the sensitivity using nanostructures. What is not so important for the cyber physical system here, but idea is to have sensors. What the point I want to make here, that if we have sensors, if we have biosensor, then probably we could make sensor network, train the sensor network, and probably have much more what you say standardized or validated automated system where the continuous monitoring or real-time analysis probably could be very useful for community-based water distribution network. This is an example where we demonstrate for the estrone or estradiol, which is an endocrine disruptor, infertility causing chemical compound. And this is now also an important emerging contaminant in EU and India. And there are no validated methods in biosensors. So we were probably among the first few groups who could go down and demonstrate using a nano immunosensor for the estradiol. We can also think about various locations. There is one EU project going with my Swedish partner. They're doing seawater quality monitoring. And we are collaborating partly on that to provide the sensor and try to see whether this can work for seawater quality monitoring for some of the emerging contaminants. And likewise, also for antibiotic residue analysis. Today, everybody is talking about superbug, also resistance to the bacteria, no new antibiotic molecules being discovered. So another application is on the various sensors for antibiotic detection. We had collaborated with the French group here on various antibiotic sensors, and then some of the devices also were fabricated, also the screen printed electrodes, and tried to showcase that antibiotic residues in milk or milk powder or also such other industrial discharge are extremely important today. And if you are able to detect them meeting the EU standards recommended, or maybe the Indian standards, which is the third one, FSSAI, if you are able to meet those and provide those sensors to the industry, probably the food safety quality aspect, which is another important EU and India collaboration opportunity, not for me, but for BITS and Telecom France, to look about, probably could be an interesting platform. So we demonstrated one such antibiotic residue sensor with this work. So these are some of the thoughts. I thought for a first interaction could be more than enough to give a flavor of what we are doing and what more. So in addition to me, there are many other things happening which we can do together. So with that, I convey my sincere thanks to all of you to listen to me patiently and have a good evening. Thank you.
Yeah, thank you, Professor Bhand, for a nice talk. I think Professor Soumyadip Bandyopadhyay have some questions.
Yeah, very nice talk. My question is, for the milk scanner, is it same as what is available in the market? Is it something more sensitive?
No, I think the market is only looking at some of the physical chemical parameters. The urea sensor is slightly different than what we have. This is more for process plant. If you're talking of urea, or which one if you have a specific question.
Yeah, the urea and adulteration, you are not working. You are working mainly the ammonia, urea, this kind of composition
Right.
which are there in the.
No, this is a thermal sensor based on the enzyme thermistor. And the market is probably visual what people have. So this we thought of keeping in mind the processing plant. If something is coming bad, it will not contaminate the whole batch, for instance. Yeah.
And for the COVID, I think you can think of something antigen antibody reaction kind of,
Sure.
paper-based detection, if that can be done.
Yeah, we
That would
can
be
think
very
about it.
important, interesting. So we can talk on that.
Yeah, thank you so much.
Yeah.
Okay. Thank you.
Yeah, I stopped sharing. Thank you so much.
Yeah. Thank you, sir, for a nice talk. Yeah. So we just go to our next talk. So the next talk will delivered by the Dr. Dominique Blouin from the Telecom Paris, France. And he is basically obtained his MSc in physics in 1994 from University of British Columbia, and he did PhD in computer science in 2013 from the University of South Brittany in France. He worked in industry for several years, and before he joined the lab CTiCPS at University of South Brittany in 2008. After a postdoc in the System Analysis and Modeling Group of the Hasso-Plattner Institute, Germany, Potsdam, he joined Telecom Paris, the Institute of Polytechnique de Paris, as a permanent research engineer in 2016. The Dominique was the vice chair of the working group 1 on the foundation of the multi-paradigm modeling of cyber-physical systems during the European cost actions. He has been a member of the SAE AADL Standardization Committee since 2010, and he proposed RDL language, which inspired the Alicia, the architecture-led incremental systems assurance framework. His research interests are foundations of multi-paradigm modeling, model management, domain-specific language, and the requirement engineering applied to the cyber physical systems development. So I'd like to thanks Dominique to accept the talk and being a co-organizer, and I'd like to start. Dominique, please.
Okay, thank you for the introduction. So I will try to share my screen. So do you see my screen well?
Yes, sir.
Yeah.
Okay, good. So, and how is that? That's okay, right?
Yeah, it's fine.
Okay, so we had as a keynote Hans Vangheluwe, who talked to us about multi-paradigm modeling, as we saw. And so basically, as you all saw, when you do multi-paradigm modeling, or even when you start modeling systems, complex cyber-physical systems, and probably also in the bio domain, is you need several models, depending on what properties you're interested in analyzing of the system. And because of that, you have many models that typically coexist together and can be modified by different people sometimes concurrently. And that's why, in order to be able to do multi-paradigm modeling, you need model management to be able to manage these models properly. So this is what some part of research that we are doing at my school, in which we are collaborating also with BITS, via Soumyadip and Rakshit, and I will talk a little bit about that basically. So here's an outline of the talk. So I will first start talking a bit about model-based engineering, where that does come from, because I think this is not something that is so well known for this audience. I will also adopt a point of view that in which we are involved. We're involved in the development of a modeling language for cyber physical systems called AADL, and I will basically show how this comes from, what are the problems we're trying to solve with this language, and then I will go into multi-paradigm modeling. So this I will go quite fast because already Hans has talked about it very much. And then I will show what are the problems in model management and talk briefly about a project that is going on to basically manage these models, and then conclude the talk. So this thing about model-based engineering starts with a problem that you can see very well in the domains of the avionics. So this is a plot of basically of the number of onboard lines of codes that you find in the commercial airplanes for both Boeing and Airbus as a function of the years. And if you look at, this is a log plot, and if you look at the slope of the line there, you find out that basically roughly the number of lines of code in airplanes is doubling every 4 years as you go to the models. And this is used typically as an indicator of complexity of these systems, because more and more functions in an airplane are implemented in software. And that software becomes harder and harder to develop, basically due to side effects and things that were not planned early enough in the development. And people have seen that at some point, like this was published in 2009, you reach a point where the system becomes so complex, there are so much errors introduced in the design that the cost increases too fast to develop these systems, and it becomes unaffordable. And there is a concrete example of that here. I have taken some numbers for the development of well-known aircrafts. Most of them are in the military because we have the figures there. And so if you look at the F-16 aircraft, it had, and the F-35, which is a model is more sophisticated than came after, you see that the ratio of the number of lines of code of the F-35 over the F-16 is 175. And then if you compare with the development effort of this aircraft compared to the F-16s, you find out that it's 300 times. So we clearly see here that these efforts are non-linear at all. So it shows a real problem. And actually what happens with the latest aircrafts that were developed, for example, by the US Army, is that they had a set of requirements when they started the project, then realized that there were so many errors introduced that they had to rework so much of the design that in the end they went over budget, and they simply decided to reduce the requirements to be able to cope with the budget they had. So this is with the standard development method. So clearly a new paradigm in development is required. Okay, and this is the same case on the European side for the A400 aircraft, which was delayed by about 10 years, and it was 6.2 billion euros over budget. And so people have studied why does cost increase so fast when we have more and more functions in a system, and they have discovered basically that it's because many errors are design errors or requirements error are introduced early in the development. So this is, for you who know, is the V-cycle model of development. So you first it's a very well used in the development of safety critical systems. So you start with capturing your requirements, then you go into your system design, and then the software architecture and the components, and then on the right hand side, then you build the system. So you start with testing it, implementing it up to the acceptance test. And people have found out that 70% of the errors are typically introduced at requirements and system design times, but they are only discovered very late at the integration test and system test times. And this is actually what causes this increase in cost and development cost that I showed you in the previous plot. Because basically you have to rework your design, and then that has impacts on the actual implementation. You have to re-implement things, and that makes things very, very expensive. And people started to look also at what are the problems, where these errors, where do they come from? And it actually often comes from what we call mismatch assumptions in collaborative engineering. So basically, for complex systems like an airplane, you will have mechanical engineers working on the airframe. You will have embedded systems engineer working on the software. You will have electrical engineer working on the electrical circuits and stuff like that. And very often there's dependencies in the models of these engineer, and sometimes inconsistency can arise, and that leads to a lot of costs. And this, for example, happened with the Airbus 380 airplane. When they first started to assemble the first airplane in Toulouse, they realized that the cables were a bit too short for the airframe, and this because two different teams, two different domains had used different versions of software and models. And so the idea is that instead of using documents as traditional methods for specifying systems, is to move to models. So everyone should be using models to represent the specification. And when you use models of a given languages, as Hans talked about, then you can start building tools to do these analysis and verify these consistency between the different models. Okay. So that's, and the analogy we do often when we talk about model-based engineering, we compare this with the compilation chain. So those of you who have a certain experience in software, remember when we're programming with assembler, then we had to specify so much details of the program that, of course, we could not be very efficient in programming. And people to solve that problem, what they did is they started thinking at increasing the level of abstraction and developing a higher level of abstraction languages like the programming languages that we know today, and let all the details be generated automatically by these compilation chains. And that's what we're doing basically with models, is that what we try is we're trying to, again, increase even more the level of abstraction, even higher than the programming code, but through these models, high level of abstraction models of the system, of its architecture. And we typically also try to separate the concerns, like we will try to have a model of the hardware, model of the software, and then see how these are joined together. And from there, then we can do some design space exploration analysis, and then rework the design in order to fix it before we actually implement the real systems. And further than that, once we know that we have a correct design in our specification models, then we have tools to automatically generate the code from these models, and we get back to this compilation chain that you can see in the bottom here. Okay. So now, what is multi-paradigm modeling? So Hans explained what it is pretty well. So obviously, it comes from the fact that for a given system, and especially for cyber-physical systems, because they are very heterogeneous, then you will need different models with different paradigms to analyze your system. So obviously, you will have many of these models that will need to coexist together. For example, you may have an architecture model here of your system. You will typically derive another model on which you will be able to do some security analysis. It can be real-time performance, etc. So you really need a lot of models, and that's where multi-paradigm modeling is involved. So this slides basically is just mostly a summary of Hans' talk. So MPM, multi-paradigm modeling, was really initiated by Hans a long time ago, and you can summarize it with a number of principles that he went through his talk. Basically, is that you should always model every part and aspect of a system explicitly, and because very often the errors are also introduced because there is some information in the head of an engineer that is not specified anywhere, and then the other engineer doesn't know about it, and that's where you have these inconsistencies. And again, as he said, you have to use the most appropriate levels of abstraction for whatever you want to do, for whatever properties you want to analyze in your models. And we have to realize that it's not possible to build a single modeling language that can capture every aspect of a system. So there's too much, it's too heterogeneous. So that means you need to combine this language and reuse these existing language in the appropriate workflow for your development. And we had a cost action that Hans also briefly mentioned in his talk. So we had an action on the multi-paradigm modeling for cyber-physical systems, and I'm going to talk a little bit about the results of this project there. So the chair was Hans, and the vice chair was Vasco Amaral from University of Lisbon. And there were the objectives of this cost action was to see how multi-paradigm modeling can be used to bridge all these different disciplines that you need to consider when building cyber physical systems. And we had basically 5 working groups in this section, and I was actually vice chair of the working group 1 on foundations. So we had 3 deliverables in this group, in this working group. So one of them was to produce a state-of-the-art on modeling language and tools and techniques used for CPS development. And this translated into a structured catalog of these languages and tools used for CPS development, and also a framework to relate and combine modeling language and tools and techniques to support MPM. And so in order to do this, especially to develop the framework, we consider 2 modeling schools of thought. So when you're doing modeling, there can be 2 different, you can basically separate this into 2 different kinds of objectives. And you can have what we call explanatory modeling and also constructive modeling. So for example, if you're a biologist, you can be looking at whatever biological species, animals exist in the world and try to classify them, to model them and classify them. In other words, you're trying to explain, you start from what exists and try to explain it by looking at what exists. And then you're in the open world assumption in the sense that that you don't know in advance what are the types that exist, and you try to infer this classification out of what exists. And for this, you use language. The biologists have developed a language that some of you may know already, like the old language, ontology web language, with a well-known tool, Protégé, that allows them to classify these species in a more easier way. On the other hand, you have the constructive approach where you do models to construct, for example, a new tools to do some specific task, right? And in this case, then you're more into building a solution for a problem. And what you do is you're in prescriptive mode, and the most important thing is it's in a closed world assumption, because you already know what are the types you want, what are the types for your domain, and you build a language that develops that. And so what we did in this cost action approach, we only took into action this explanatory phase. So in other words, we developed an ontology of multi-paradigm modeling for cyber-physical system in order to better understand how people model cyber-physical systems for their development. Okay, and the second phase, which would be constructive, basically to develop a solution to manage and relate all these models in the modeling language, was led in the second stage, which is what we are currently working on in our team. So the result of this action was an ontology of MPM for CPS. So we have used the Protégé and the ontology web language to capture this ontology. And in order to make this reusable, we have separated this ontology in different domains. So we had a domain for multi-paradigm modeling, where we only capture what is multi-paradigm modeling, an ontology of cyber-physical systems. So Akshit has been also involved in this project, and we'll probably talk a little bit about that during his presentation. And finally, we have another ontology that integrates these 2 domains, that relates with the formalism that you use to analyze the system, what are the parts of the system that you can consider via these notions of viewpoints, basically. And out of this ontology, we could create individuals conforming to the types of these classes and properties, where we created this catalog of modeling languages and tools for cyber-physical systems development. And we could also generate all these deliverables from this ontology. And in order to better come up with this classification, what we did is we considered a number of example cyber-physical systems development environment. So for example, one of them is the Hasso-Plattner Institute, the Cyber-Physical Systems Labs that we have at the Hasso-Plattner Institute, where we develop basically robots. We can model robots and how they can interact together for using them in a kind of production plant system. Another system, very different modeling system that we have used as an example was also a development environment for an autonomous multi-agent system called AnSyMo-based cyber-physical systems from the Charles University. So by looking at these existing development environment, looking at what are the models that they use, what are the language that they use, how they are combined, everything, we came up with this ontology. Okay. And now, what is model management? And so, this ontology, as I said, the purpose is that once you understand what are the language involved and how they are combined in the practical case, then you can come up with a solution. In other words, a language to model how this combination happens to better support this combination for development. And so what we do here is basically when you do model-based engineering with several models, what you do is to the traditional V-cycle model where you have requirements engineering, system design, software architectural design, you add another line of the V where for each of these models that you have, you can perform with tools different verification and validation activities because you have specified your system with these models, okay? And on the side, you do the same for the test. You also model basically the assurance case of the system so that you have evidence that your system does what it should do. And this allows to reduce these costs. And there are typically two different axes that we consider when we do this model management. And we have what we call the horizontal axis, where basically for a single system, you will consider models of the different domains that you want to analysis. It can be mechanical, electrical. And you have another axis where you do a change in abstraction, which is what Hans talked about. So you start with a high-level model that does not have all the details of the system, but at which level you can still do some analysis, and then you refine it by considering more specific hardware. And once, as I explained, once you have this more detailed models, you can go into code generation. So at our school, we also work on a tool called Ramses, which is a code generator. So we start with these deployed models of the software and hardware, and automatically we generate a big portion of the code. And then we go back to this compilation chain. So as we can see, we have a lot of, on the V-cycle model to the normal design, we add an activity of verification with these models. So because you have all these models, you can have other activities that you will need to add in this V-cycle is to manage the model. And that's why we have that diagram here where you show these model management activities that goes along the V-cycle. So each square here represents more or less a models, and the line between them are the relationships. So typically, you will start with a set of requirements that you also express as models, and you start your design. And then as you do your design and you do your verification, you may even discover, for example, that there are some errors into your requirements. So then you may go to a new set, change your requirements, and do design, etc. So that means you also have to manage not only all these models at the different levels of abstraction, different domains, but even also maybe some different version of these models that you want to be able to store and to remember during this. So as you can see, model management is there's a lot of things that you need to capture. First, the models you use, their links, and also different versions that you may be using. And so what are the needs when we want to do this model management? So we need to know what are the employed models that we have, what are the language, what are the tools, how they are related, and there can be very different kinds of relationship between these models. And also an important aspect is what is your development process? So in multi-paradigm modeling, we say that not only we should model everything, but also model the development process, which is what Hans showed with this activity diagram. And another important aspect that you need to configure is a notion that we call the ASOT. It's an authoritative source of truth. So basically, and I will explain this in these diagrams. So this is an example taken from a project in which we developed a modeling-based process for systems in the railway domain. So you typically may have a model of what is called SysML at the high level, system engineering level. And then you may decide then that you want to do some embedded system real-time analysis. Then you go to another language called AADL that we work on. And depending on the process you have, there's a very different kinds of relationships you may have. For example, you may decide that engineers will work on this SysML model, and then by hand, they will automatically create this AADL model and have some kind of trace links between these models. You could have also decided that you would synchronize these models automatically using some model transformation tools. Sometimes you may have, you may allow that only if you do, you cannot modify this AADL model without and then you have a unidirectional relationship here, and so this shows basically that you can have all kinds of transformation there, and then there's also a problem of information overlap. Very often these models have contain a similar overlapping information contained. And that's why you have to make sure that these models remain consistent, and so especially in the case that they can be modified by a really different person. So all this needs to be managed properly with proper model management. Okay, and of course we need the concept of authoritative source of truth to decide if you have several models that have shared duplicated information. If you have an inconsistency that happens between these two models, which one has the truth? So this is an important, and we work typically in a configuration where we are architecture centric. So we decide, for example, if we have an architecture model, then we go always to other domain models. Then we do not allow to have a change between these domain models, but if you do a change in a domain model, it should go back to the architecture and then propagate the change to the other models. So depending on how you decide to have this configuration, then that also changes the model management that you're going to do. Okay. So now there is actually approaches that have been developed already for model management. It's called the mega modeling. So basically it means modeling at the large. So what we do basically is we model the models that we have, and we model their languages and all these relationships. So there's a number of mega modeling that have been already developed for that, and I will only show, I will go very quickly over that, but basically you can have, maybe I'm running out of time. Huh? Soumyadip?
Yeah, it's a 3 minutes more.
Okay, so I will go, there's a number of modeling management approach that already exist, including the one that that Hans briefly mentioned here, where we also link to all the models that you can transform. You link them to the how they are taken as input and output of your development process. And we have this project. I will finish by talking at this ongoing project we have, which is an architecture-centric model management, where we're currently reusing all these, the best of all these approach to develop a model management language where we can capture all these important notions of what is the source of truth, what are the change, which team can change which model when, and also integrate the development, a model of the development process, and manage these change policies. Okay, and then we're prototyping this project. Actually, what we do is we try to do this with real languages. So we have this AADL language for embedded systems. So you will have a presentation on this modeling language by my colleague Etienne tomorrow. So instead of prototyping with very simple languages, we try to prototype with real code generation tools like Ramses and this AADL language. And this also allows us to discover, to really validate our approach better. And you will see also another presentation done by someone from our team where we have compared 3 different model transformation tools and show that when we use these complex, the realistic languages, basically these tools are not yet ready for industry. So that will be presented also tomorrow by my colleague Hannah. Okay, so that's about for this presentation. I just wanted to show you that when you do multi-paradigm modeling, basically you need a lot of models, and you really need to formalize also with another language what are these models that you're using, and so that you're able to better manage these models and avoid these inconsistency that can easily happen between 2 different models, especially when they are modeled by different teams. And the thing is, with this you really need a language where you can customize these language that are used, because every company, every team has its own language that they decide to use, and they may combine these things differently depending on what development process they are using. So that's why it's quite important to formalize these things, and which is our ongoing project on that. Okay, so I can stop here maybe.
Well, Dominique, I have just one question, and then I go to some other audience. So from Slack channels, I just check. No, there is no questions from the Slack channels. From the speaker rooms, Professor Shorkar.
Yeah, I would like to ask just some question about slide 18, 19. Yeah, I think okay. Okay, this is exactly the one that I was looking into. So you have hand-in-hand validation activity going on around each of this modeling, which finally leads to the code development. That's what I have gathered. Now, is it that at every level, let's say right at the top level, requirement engineering and requirement validation, now is it a completely or at least semi automated process, or is it that you deploy simply human activities for your validation?
So there's a lot of human activities, but the idea here, because the idea here is that first of all, if you have requirements that you capture in natural language, and then you move from capturing these requirements with a modeling language, already you are capturing some errors there, because the modeling language is more formal and will not let you will force you to be more precise in your requirements, and will not and less error will already be introduced there. After that, there's also the requirements engineering research community is very rich, and many people are working on methods and tools to even analyze your requirements to see if you have inconsistency within them and things like that. And this is actually what we are doing also with BITS, with Soumyadip. We're also working currently on this approach based on the requirements language for the language. But still, there's really a lot to do at the requirements engineering, and there's a rich community working on that. But if you first model things, then you can build tools. If you don't, working on natural language is really too difficult. I don't know if that answered the question.
Mr. Shortcut?
Yeah, am I audible now?
Yeah.
Yeah.
Okay, so just if you go to slide 20 or so, where you have been speaking about versions at the same level.
Ah, yeah, here, that's the model management activities.
Yeah, so in this case, I noticed that, so is it that different groups in a particular level across the horizontal progress, is it that different teams build this V1, V2, V3, and then you try to analyze and try to find out consistencies among them from requirement side? Is it that different, what I am trying to say, these versions are essentially devised by different set of people or the same set of people?
No, it can be in this case, it's actually for the whole team. In other words, like you start by capturing requirements at a high level, and as you go into more detail, starting to work on your design, then you may discover changes, right? And you decide that, okay, no, finally I have to make this design decision and I need new requirements, or you may even find that your initial requirements are incorrect. And then because of that, you may decide to go to a new version of a requirement sets for the whole team, for example. And then you may want to capture also that you have had these different versions, and then you would have different mega models, which each version of the model with trace links that indicates what has changed, for example. This is just to show all kinds of activities you may need to have to model, to manage all these models during development, basically.
Hello?
I don't know if that's...
Sorry, I'm sorry. It gets unmuted automatically. I muted automatically. Okay, so I have come across a particular work where they have recommended. It's about avionics. Yeah. So they recommended that different set of people be deployed to understand the requirements in their own respective ways, because it's natural language. And they come up with different versions of this at the same level, and then they try to see some kind of equivalence or containment analysis, not necessarily formal, but they have insisted on formal ones. So do you feel that that could be something relevant, that the fact that it's natural language, so different set of people, and it is amenable to different kind of interpretations, and therefore it is necessary to deploy different set of people to apply their own perceptions about the requirements? Do you feel that could be a relevant one?
Yeah, well, I would say that it's quite typical. We're talking most of the time about different stakeholders of the project, right? Because you have each stakeholder may have different goals or different needs, and then what you're trying to do when you do your requirements engineering, you're trying to mitigate. Sometimes they have contradictory needs. You have a marketing one, a cheap product, and people for safety want a safe product, and these may have some contradiction. But in your case, when you're saying that you have the same set of requirements developed by totally different people, so are these the same stakeholders or not?
The user specifies the requirements. The designers have their subset or subgroups trying to understand the requirements, or trying to put some formal models out of the requirements, but they work independently to come up with different versions they may differ in their respective perceptions, and that's what reveals some bit of inconsistency in the requirements or some gray areas which needs to be refined further. So I was just thinking whether this could be also an approach.
Yeah. So we could that's quite interesting. So it seems to me it's a bit like a pair programming or something where you have two people doing two different teams doing the same things, but see if they come up with the same solution or something like that, right? But the idea is that you could build model management to manage this properly. Actually, yeah. That's a good point. I'm not aware of such process. In which company this was used?
Yeah. So it's a work on avionics. I am not very, immediately it's not there available in my fingertips, but I hope through Soumyadip I'll be able to send you some this thing. So no, that interested me because, we were involved in equivalence checking. And so I thought that along this horizontal, line, when you have various versions which originate from the same input, you have a scope for checking the equivalence and trying to find out whether the input would be. So I was just trying to find out what are the different kinds of paradigms. Say when you go along the vertical axis, what kind of reasoning mechanism, whether it will be language containment or equivalence checking. So I was just trying to figure out that possibly along the horizontal direction, you have scope for equivalence checking.
Yeah,
so I just,
actually,
yeah.
yes, sir. Actually, there is a obvious scope because when the model transformation takes place and when it actually gives the code level, so in the model transformation level, there is a scope of the equivalence checking. So what the Dominique is showing in the requirement engineering, there is obviously is a scope.
Yeah, but there is one thing that is important, that, at what level we start applying the automated or semi-automated tools, and at beyond what level we'll have to be satisfied with human reasoning.
Yeah.
At which level of abstraction you mean?
Yeah, at which level of abstraction. That means in your this V diagram, if I may call it, so in this diagram, up to which level you have been able to do it in computer assisted or fully automated tools, and beyond which level you had to be content with human reasoning.
It totally depends on the properties you want to verify. Of course, at the very high level of the requirements engineering, you're interested to see, first of all, typical properties to see if your requirements are consistent, if you don't have inconsistent requirements, to see how also if you got your requirements coverage and things like that. But then once you go into more details, for example, if you go into component details design in the architecture, then you can start to do some much more fine analysis, like for embedded system testing, if your system can be schedulable, if your threads can be scheduled, if you have the required processor resources to schedule all these threads or to execute all these your application function and stuff like that. So the properties you will analyze will of course depend strongly depend on the level of abstraction you're at on the activities, basically.
Well, we just almost close these sessions. So actually, we are already over our timings. So thanks, Dominique. Thanks for your talk.
Thank you very much.
And thanks all of you for attending this sessions. And now we'll close these sessions and we'll go for our second session. So second sessions will start from 6 o'clock So this 15 minutes is a virtual coffee break. From the 6 to 7, there is a session 2. The chair is Hans, Professor Hans. And there is a 2 track. One is student track and another is a BioCPS track. So thank you.
So everyone can meet on the Gather room. We have made a virtual room on Gather, the platform, and the link is there in the Slack channel.
And
all the participants can meet on Gather.
Is it possible to paste the app, that is the link of the Gather tool here?
I will put it on the YouTube comment section, sir. That is
okay. Okay,
sir. So
okay.
this.
Thank you.